Hello, welcome to lecture number 2, Elementary Number Theory, Divisibility, Part 2. Okay, I will continue our discussion from last time with introducing some new theorems, which are very simple, but they are very handy in what is coming in the future. The first theorem is this. Okay, if a, b, and c are non-zero integers such that a divides b and b divides c, then a divides c. In other words, the following statement is true. For all, this symbol means for all, a, b, and c belonging to the set of integers except number 0. If you know that a divides b and you know that b itself divides c, then if you want to, you can conclude an a divides c. This is called, sometimes we say that divisibility is a transitive relation. For example, if I know number a is equal to b and I know number b is equal to c, if I want, I can conclude that a is equal to c. So we say equality is transitive. For example, if I know that a is less than b and I know that b itself is less than c, if I want to, I can conclude that a is less than c. So this means equality as a relation, inequality less than as a relation, and divisibility as a relation, or what is called transitive relations. We will talk about these properties of relations later extensively. Okay, so this is what we want to show. So let us have a proof. The proof is extremely simple, but I think it is good to know, to go through the proofs carefully in the beginning, okay? Okay, so we know that A divides B. According to the definition, this means there exists a Q in Z such that the number on the right, B, is equal to the number on the left, A times Q. And we also know that B itself divides C. So what does it mean? It means that there exists an integer. Okay, a common mistake is that sometimes people call it Q again, but when you call it Q, it means that you are forcing this cube to be the same as Q as the previous one. But we don't have that guarantee, so I will call it a new variable. So let us say Q prime. Okay, in Z, such that the number on the right, in this case C, is equal to the number on the left, in this case B, multiplied by that integer Q prime. But if you see, what I want to understand is the relation between A and C. So somehow I have to connect A directly to C. And that is very easy. The only thing I can do is just to take this one and put it here. So then what happens, this means that C is equal to, instead of B, I put AQ, and then I multiply it by Q prime. But this is now simply C equals to AQ Q prime. But because Q is an integer, Q prime is also an integer, this product Q prime is definitely an integer. So let me give it a new name. So let me call that product to be capital Q, yes? So then what happens, this becomes C equals to A capital Q. And then important thing is that capital Q is in Z. So this means that A multiplied by an integer is C. This means that A divides C. And that is what we want to prove. Okay, very simple. Another theorem that we want to discuss today, and very simple, is this. If I have A dividing B, and if I know that M is an integer, if I want to, I can multiply both sides by M, and still this relation holds. But in this case, if I want, I can just multiply one side by M, but that one side should be the right-hand side. So this means that if A divides B, if I want to, I can multiply the left and the right by an integer M and conclude this, which is true. If I want, we can multiply only one side by M, but that one side should be the right-hand side. This is also, so if this is true, this one is also true. So compare it with equality. In equality, if I want to multiply the left-hand side by M, I have to multiply the right-hand side by M if I insist to keep the equality intact, yes? But in the case that my relation is divisibility relation, I have two choices. Sometimes I need to multiply both sides, that is working. But if I want to multiply one side, that is working provided that I multiply the right hand side by that factor, not the left hand side only. So in other words, if A divides B, there is no guarantee that MA divides B. Okay? Okay, so let us see the proof. The proofs are very simple and elementary, but it is good actually to go through them in the beginning. Okay, so if I know that A divides B, this means that there exists a Q in Z such that the number on the right is equal to the number on the left multiplied by Q. Okay, so I multiply both sides of this equality by m. So then it becomes mb is equal to maq. Okay, then I can interpret this equality in two different ways. Okay, I can interpret it as mb equals to, let me write it in this form, ma times q. Then what does it mean? It means that this number multiplied by an integer is equal to this number. So this means that MA divides MB. But again, the same relation can be written slightly differently in this form. I can write it as MB, but instead of grouping M and A together, I can group M and Q together. Okay, and I can write it as A times MQ. But now M is an integer. Okay, Q is also an integer, so this means that this product is an integer. So an integer multiplied by A gives me MB, so what does it mean? It means that A divides MB, and that is the proof for the second part. Okay, the next theorem. A, B, and M be non-zero integers, okay, and we know that A divides B. And we also know that when I divide A by M and B by M, these numbers are both integers. Then it means that I can divide both sides by M and conclude that A over M divides B over M. Be careful, A over M and B over M should be integers, otherwise this relation does not make sense. This relation makes sense between two integers. And I can divide only one side. So I am allowed to divide both sides, or I am allowed to divide only one side. But if I want to divide only one side, that one side should be the left-hand side. Okay? So if you know that A divides B, and you know that A over M and B over M are both integers, then you can either divide both sides by M if it is beneficial. For example, you are solving a problem in which this is useful. Or you can divide one side provided that one side is the left side. Sometimes this might be useful in your problem. Okay, I am just tabulating them. I'm itemizing these theorems for you so that I can use them freely in the coming lectures. Okay, the proof of this one is also very simple, and I want to leave this proof as an exercise. You just try to do it yourself. It is very simple. Okay, now let us solve an example. Determine all integers n such that n to the fourth minus 1 divides 3n squared plus 3. Okay, this is not hard to see that you can factorize this using the conjugate rule. You can also pull a 3 out, factor 3 out, okay? And this will be useful. Why? Because the left-hand side becomes n squared minus 1 times n squared plus 1, and the right-hand side, so divides. On the right-hand side, I factor a 3 out. This becomes n squared plus 1. Now, exactly according to the theorem we just learned, I can divide both sides by this expression. In other words, I can cancel this from both sides. Why is that possible? Because when I do the cancellation, the leftovers are integers. That is extremely important. When I do this cancellation, the right-hand side is 3, which is an integer, and the left-hand side is n squared minus 1. If I assume n is an integer, n squared minus 1 is also an integer. So this cancellation is indeed allowed. Okay, so I cancel that one. Okay, and then I conclude that n squared minus 1 should divide 3. But that is very simple because 3 is a prime number, so the divisors of 3 are not that many. So plus or minus 1 or plus or minus 3. So let me write or to be precise here, okay? So then I have to start solving this. N squared minus 1 equals to minus 1 gives me n squared is 0. So this means that n is 0. So that is one option. And then I have n squared minus 1 equals to 1. This gives me n squared is equal to 2, which will not give rise to any integer solution. N is plus or minus square root of 2. And then n squared minus 1 is minus 3. Then it means that n squared is minus 2, which is not even possible in the realm of integers or even real numbers. And then the next one, n squared minus 1 is 3, which gives me n squared is 4. And then it means that n is plus or minus 2. And these numbers are also integers. So if I want to write the all possible solutions, 0, plus 2, and minus 2. If you test that, if you put 0 here, the left-hand side becomes minus 1, the right-hand side becomes 3, which is true. And if n is 2, or minus 2, it doesn't matter because these are even powers. So the left-hand side becomes what? 16 minus 1 is 15. And the right-hand side becomes what? 3n squared plus 3, which is let me double check. Yes, yeah, that's correct. Because if I put plus or minus 2, the left-hand side becomes 15. The right-hand side also becomes 15. Yes, that's correct. So all these answers are indeed acceptable. Okay, the next theorem tells you that a, b, and c are non-zero integers, and we know that ab, the product ab, divides c. Then the conclusion is that both a and b divide c. So it means a divides c and b divides c. So in other words, if a, b, and c are non-zero integers, and we know that ab divides c, if you want to, you can conclude both a and b divide c. Okay, let us look at the proof, okay? Okay, so let us do the proof. What do I have? I know that AB divides C. So according to the definition, this means that there exists a Q in Z such that the number on the right C equals to the number on the left AB multiplied by that Q. But this equality can be interpreted in two different ways. Yes, I can write it in this form, ABQ, putting B and Q together, or if I want, I can interpret that as B times AQ. Okay? But because B and Q are integers, BQ is an integer, so this means that A multiplied by an integer is C, so this means that A divides C. But this can also be seen that A times Q is also an integer, so then it means B times an integer is C, so this means that B also divides C. So this is the proof, okay? Okay, as a remark, this is simple, yes? What does the previous theorem means? The previous theorem states that if an integer is divisible by the product of two integers, then it is divisible by each one of them individually. Of course, using mathematical induction, you can generalize the previous theorem to any finite number of non-zero integers as follows. Meaning that if you know a number is divisible by a product, then if you want to, you can conclude that this number is divisible by each one of these numbers individually. Yeah? Yes, that is the same theorem in words, expressed in words, rather than mathematical symbols. Okay, the next theorem, which is also very simple but very handy, is that if I know that I have non-zero integers a, b, c, and d, I know that a divides b and c divides d. If I want to, I can multiply the left-hand sides, and I can also multiply the right-hand sides, and be sure that this relation is also true. So in other words, if I have two divisibility relations, I can multiply the left-hand sides and I can multiply the right-hand sides, and the divisibility still holds among the products. Okay? So for example, if I know A divides B and I know that C divides D, this is not true that I can conclude, for example, if I add them. Yes, this is up to you as an exercise to bring a counterexample. Bring an example that this holds, but this does not hold. So this means that adding two divisibility relations side by side might give rise to a non-true statement. Okay, so that is not valid. But if you want to multiply them, it is valid. Okay? Okay, so why this is true? Again, very simple. So you tell me that A divides B, so this means that I am allowed to conclude the existence of a Q in Z such that the number on the right is equal to the number on the left multiplied by that Q. You also tell me that C divides D. This means that there exists an integer which is probably not exactly the same as the integer before, so let me call it Q prime, so that the number on the right is equal to the number on the left multiplied by that integer Q prime. But what is my goal? My goal is to prove the relation between AC and BD. So this motivates me to multiply these both sides of these equalities side by side. So if I know that this number is equal to this, and I know that this number is equal to this is guaranteed that the product of these two numbers is equal to the product of these two numbers. Yes, so if I multiply them, it becomes BD equals to ACQ Q prime. But now everything becomes clear. Yes, on the left hand side I have BD, on the right hand side I have AC multiplied by Q prime, but Q is an integer, Q prime is an integer, so it is guaranteed that Q prime is also an integer. So let me, for example, give it a name. Let me call this one capital Q, but importantly is that the important thing is that this capital Q belongs to Z. So now what do I have? I have BD equals to AC times Q, so then it means that AC divides BD. Yes, because AC multiplied by an integer is equal to BD. That's exactly the meaning of AC divides BD. That is very crucial to see here that, for example, let me write it with a different color here. Let us say that you are careless and you just write Q again instead of Q prime. Okay, what does it mean then? Then you can prove something which is not correct. For example, if I naively, so let me write it with a different color. Let us say that when you say C divides D, you write it as there exists and you use the same letter Q, Z, such that D is equal to CQ. Then what happens? Let us say that, okay, I will take this one and add them side by side. Then what happens? This becomes B plus D. The right hand side, because now the letter Q is in common, I can pull it out, factor it out, it becomes A plus CQ. And then you wrongly and mistakenly will conclude that because A plus C multiplied by an integer is B plus D, then it means that A plus C divides B plus D. Okay? So you might think that if this relation holds, you can conclude this relation holds as well. But immediately we can bring a counterexample. Yes, for example, let us say that we know that 1 divides 2. I am giving the role of A to 1. I am giving the role of B to 2. And I know that, for example, 3 divides 9. Yes, I am giving the role of C to this, I am giving the role of D to this. Both of them are true. 1 divides 2 is true, 3 divides 9 is true. But let me add them side by side. 1 plus 3 becomes 4, divides 2 plus 9 is 11, which is false. Yes? So I hope that you agree with me that this is not correct. If this is correct, this conclusion is not always correct, as this counterexample shows. What is the mistake in this proof? The mistake is that you have written q again. So that is why it is extremely important to write q prime or any other variable so that you can see the difference. Here, if I write one of them q, one of them q prime, if I even add them, then what will happen? It becomes aq plus cq prime, and there is nothing to factor out. So be careful when we say q and then I write q prime. Q and q prime are variables that they adapt themselves according to the numbers given. It doesn't mean that q and q prime are definitely not equal. They might be equal, but they also have the chance not to be equal. But if from the beginning you don't put q prime here and write q and q, it means that you are forcing that the same q that works here will work also here, but we don't have guarantee for that. So that is a subtle, important thing that I want you to pay attention to it. Okay? So this green part is not part of the proof. Okay? Okay, the next theorem, which is also very important, allows us to raise both sides of a divisibility relation to any natural power that we want. Okay, so this means that if a and b are non-zero integers and I know that a divides b, and if n is any natural number, then if I want to, I can conclude that a to power n also divides b to power n. Of course, here it is more or less clear that n should be a natural number, because if it is a negative integer, then a to the power of a negative integer is not guaranteed to be an integer in the first place, and we know that this relation only holds if I have integers on the left and on the right. Otherwise, this relation is not even defined. Okay, the proof is also very simple, yes, because that is more or less what we learned in the previous theorem, repeating itself n number of times for the same relation. Or we can use mathematical induction to prove that, of course. Okay, so for example, if you want to prove it, you can prove it using mathematical induction. For example, let me call this statement a to the power of n divides b to the power of n, and I want to test it for n equals to 1. So if I replace n with 1, then it means a to power 1 divides b to power 1, which is true because of my assumption that a divides b. Now let us say that k is a natural number, and I assume that p of k is true, meaning that I know that a to power k divides b to power k, assumed to be true. Then I want to prove that for the next natural number this is also true. So I want to prove that this relation holds for a to power k plus 1 divides b to power k plus 1 to be proven, yes? But that is also simple, yes? Because my assumption tells me that a to power k divides b to power k. My assumption also tells me that a divides b, but we just learned in the previous theorem that if I want to, I can multiply these relations side by side. So then it means a times a to the power of k divides b times b to power k. So then it means that a to power k plus 1 divides b to the power of k plus 1. Okay, that's a very handy theorem. Okay. Okay, as another exercise, an example, very simple. Let a and b be non-zero integers such that a divides b, and we know that m and n are natural numbers, but we also know that m is less than or equal to n. We want to show that a to power m divides b to power n. Remember, m is the smaller one. Okay? So this means that the previous one told you that if you know a divides b, then you can raise both sides to the same natural power, a to the power of n, b to the power of n. This tells you that if you have this relation, you can raise to different powers, yes? For example, you can raise the left side to power m, but the right side to power n, even if the m and n are not equal. but the left hand side one, m, should be less than or at most equal to the right hand side one, n. Okay, which is something different from equality, because in inequality, if I know that a equals to b, then if I raise the left hand side to power n and I want to keep the equality, I have to raise the right hand side to the same power of n. But here apparently I have a little bit more degree of freedom. Okay, so let us prove this one as well. Okay, I can prove this this problem from scratch, meaning using the definition of divisibility once more. But my goal is that you train yourself to use the previous theorems rather than starting everything from scratch every time. Okay, so what do I mean by that? For example, if you tell me that A divides B and you tell me that M belongs to N according to the theorem we just learned today, we can guarantee that a to power m divides b to power m. This is what we learned today. What we learned last lesson is that if m and n are natural numbers and I know that m is less than or equal to n, as I know now, I can conclude that b to power m divides b to power n. This is what we learned in the previous lesson. Now again, today we learned that divisibility relation is a transitive relation. So we know that this number, whatever it is, divides this number, but this number itself here divides another number. So by comparing these two, if I want to, I can conclude that the first number, a to the m, divides the last number, b to the n. So here, this is important for me that you learn to do it in this way. Of course, here you can go and start from scratch by using the definition of divisibility, and it works very simply. But my preference is that you learn how to use these theorems that we have learned so far to be able to do things faster. Okay? So that's why I prefer you to do it in this way. Okay? Okay, let us do a simple but I think informative example here. So the question is that let a and b be non-zero integers such that a divides b and we know that b squared divides ac. Show that a divides c and b divides c. Okay, again, of course, you can go and start from scratch using the definition of divisibility. And of course, if you really forget about the theorems, no problems. You can go and use the definition, of course. But I want you to train yourself to remember these theorems. Okay, so I don't want to start from scratch. I want to try to use the theorems that I presented here as much as I can. Okay, so for example, let us concentrate. I have two assumptions here. I know that a divides b. I know that b squared divides ac. My goal is to prove a divides c for the time being. Forget about this one first. Okay, what I do, I would say that because you tell me that a divides b, I am allowed to conclude that a squared divides b squared, according to the theorem we just learned. Okay, but now look. This is what I can conclude. This is what you are giving to me again. You are telling me that b squared also divides ac. Using transitivity, I can conclude that a squared divides ac. Is that right? A squared divides b squared itself divides ac. So, by transitivity, I can immediately conclude that. But can I simplify both sides by a? The answer is yes, because the leftovers are still integers. So what I will do, I will divide both sides by a. The left-hand side becomes a, the right-hand side becomes c. A and c are integers, so the leftovers after simplifications are integers, so this division is indeed valid. And I conclude a divides c. So efficient and so fast. What about the other one? Okay, so let us think about the other one as well in this way. Don't start from scratch. Okay, now again, I will start from here. I will assume this is true, this is also true, this one I want to prove this time. So I would say that when you tell me that a divides b, what I can do, I can multiply both sides by a. Why? Because we also know that A divides itself, and we just learned that if I have two divisibility relations, if I want to, I can multiply them side by side. Okay, so this becomes A squared divides AB. Okay, so this is what I have. Okay, let me see. No, apparently this is not working. So let me clean this. Okay, let me do it the other way around. Okay, I will assume that of course you have given me A divides B. I also know myself B divides B. So I multiply them side by side, so it becomes AB divides B squared. This is what I get. But you also told me that B squared divides AC, so B squared divides AC. Then again, using transitivity, I can conclude from these two that AB divides AC. Okay? And then I can divide both sides by A. It is possible here because the leftover on the left is B, the leftover on the right is C after cancellation, and both of them are integers. So I am allowed to conclude that B divides C. So you see, I am using those theorems, simple theorems, to prove them without going back to start from scratch. Okay, there is a very important remark here. The converse of the previous theorem is also true. Specifically, this statement is true. It means that if A and B are non-zero integers and n is a natural number, and we know that the nth power of A divides the nth power of B, if you want to, you can conclude that A also divides B. So for the time being, let us assume the truth of this claim, but if I want to prove it, we have to wait a little bit that we know more theorems in number theory. But I just want to tell you that this the proof is not just using the definition, because if I just want to use the definition, the assumption that A to the nth divides B to the nth allows me to conclude the existence of a Q in Z such that the number on the right is equal to the number on the left multiplied by Q. But now I want to conclude something about A and B, so this motivates me to take the nth root from both sides. So far so good. The left hand side becomes B, the right hand side becomes A, the nth root of Q. So here I cannot conclude that A divides B. That's important to understand. Why? Because there is no guarantee that this number is an integer even if Q is an integer. So I need to prove something stronger. I want to prove that not only this Q is an integer, but it is equal to an nth power of another integer, so that after taking the nth root, it becomes an integer again. Okay, so I just want you to know that the proof of this theorem using the definition of divisibility will not work in this way. How it works, it is not using the definition of divisibility directly, so we need more theorems to be able to prove that. But I want you to know that the converse of the theorem is also true, meaning that from this you can conclude this whenever you need. But let us defer the proof for a little bit later lesson. Okay, so now let me give an example that you can use this one as well. Okay, so in this example, A, B, and C are natural numbers such that A to the B divides B to the A, and B to the C divides C to the B. We want to conclude that A to the C also divides C to the A. Okay, again, as I told you, I do not want to start from scratch. I want to use the theorems so that my skill improves actually. So A to the B divides B to the A. And A and B and C are all natural numbers. So I raise both sides to power C. So then it becomes A to the power of B to the power of C divides B to the power of A to the power of C. Then this means A to power BC divides B to power AC. Let us call it number 1. Okay? And now I start from the other one. B to the C divides c to the b, I raise both sides to power a. So then it means that b to the power of c to the power of a divides c to the power of b to the power of a. But then this means b to the power of ca divides c to the power of ba. I call it number 2. But can you tell me, from number 1 and 2, what can I conclude? Look, here I know that this number divides this number. But do you see that this number is exactly this number? The only difference here is that we have CA rather than AC, so they are the same numbers. Okay, so this means this number divides this number, and this number itself divides another number. So this means that according to transitivity, I can conclude that this number, the first number, divides the third number. Yes, so this means that a to the power of bc divides c to the power of ba. But I can take the bth root. What do I mean by that? The left hand side can be written as a to power c to power b, and then the right hand side can be written as c to power a to power b. And now we just learned that if I have, let me write it with capital letters that are not confused with these ones. If I know that a to power n divides b to power n, and if n is natural, so you can, if you want to, we didn't prove that, but I told you, trust me on that, this is true, and I can get rid of these exponents. So now here I can get rid of these exponents because the exponents are natural, and what is left for me is a to power c divides c to power a, and that is what I wanted to prove. Okay, so the lesson for today is finished, but as I promised, I designed some problems that you can solve according to the knowledge you acquired during lectures 1 and lecture 2. And I have divided the problems into the bronze level, silver level, and gold level. And we also have one more level, which I will call it diamond level, but we do not have any problem of that kind here today. So you see there are 6 problems. These are not hard problems. I mean, very straightforward problems. You can work on them if you really want to learn this topic. You have to practice a lot. I don't know if I can find a way, because on YouTube it is easy to give you a link to this PDF file. I will try to find a way that I can share it in TikTok with you, but to be on the safe side, you can take a screenshot from this page that you can see, so that you can start working on the problems. Okay, so on this playlist we have 2 videos now, 2 lectures, but now I will produce 6 short videos. Each video will discuss the solution of one of these problems. After those 6 videos are done, then I will continue another lecture. And the structure will be the same. 1 lecture followed with 1 or more tutorial sessions, and then continue, hopefully, if I see that these lessons are well received, definitely I will continue them. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.